Hello. In the prior section, we began our first full investigation of a hypothesis test. I'd like to just go over one of the homework questions because it allows an opportunity to discuss what a p-value really means and make sure that we're understanding it. So from problem number 31 in the prior section's homework, you worked out the following. You developed the hypotheses, you found the test statistic, the z-score 2.83. You got the p-value 0.0023. So when you get this p-value 0.0023, what does that mean? What does 0.23% actually represent? Well, what it really means is it implies if the mean truly is 30, the probability of getting the test average or the sample mean of 31 or more is 0.23%. That's pretty unlikely. So then there's two possibilities. The first possibility is that the mean really is 30 and we just happen to observe an extremely rare event of obtaining a sample mean of 31 just by random chance, and that can happen. 0.23% is low, but there's the probability of winning the lottery is extremely low, but somebody will win it, so it could happen to someone. The other idea is maybe the average really is not 30. We would reject the null, and most likely the real average is something closer to what we observed, probably closer to 31. So you'll notice that the distribution maybe isn't centered about 30, maybe it really is centered about 31, and we just happen to observe a very ordinary event. And those are the two possibilities, and there is no way to know which one is the true reality. That's real life. We don't know, we're testing it, and so we make our decision based on probability, based on odds. We'd say the probability of this occurring is so low that we probably don't believe that we observed a very rare event. We probably observed a very ordinary event that had its center not at 30 but at 31. And that's really what the basis of statistics is set in, is to determine what we just observed. Is it unusual or not unusual? In the prior lesson, we decided to either reject or fail to reject the null hypothesis by finding the p-value corresponding to a sample statistic, a z-score, and comparing that to a predetermined level of significance. So one can always do the process above, and it will actually be the only process we use going forward. However, another way to accomplish the same thing is to determine something called rejection regions ahead of time, based on that significance confidence level, and see if your z-score falls in the rejection regions. So the idea is, let's set our threshold z-scores and find if our z-score is further, is a large enough number past those threshold z-scores, then we've observed something unusual enough. We don't even need to calculate the p-value because we know we're already past that threshold z-score, which we call the rejection region. So the rejection, or also known as the critical regions, are the range of values for which the null hypothesis is not probable. If a test statistic falls in this region, the null hypothesis is rejected. The critical z-scores, or z0 is the critical z-scores, is a value that separates the rejection region from the non-rejection region. Essentially, the rejection regions are the ones where the probabilities are so small they are less than the confidence or the significance level that we would be talking about. So what we need to do is we need to find what those rejection regions are that typically occur, and those are going to be at the 5, 1, and 10% confidence levels. So find the critical value in rejection regions for a left-tailed test with a confidence of 5%. So we want to know, if we're doing a left-tailed test, what is the z-score at which the probability of the area to the left, the area to the left of it is 5%. Well, we can use inverse norm. Inverse norm, area to the left is 0.05, mean is 0, standard deviation is 1, and when we run that, we get negative 1.64. This means that any z-score that is below negative 1.64 will have a probability less than 5%, and so that means that it would be a reject the null situation. So it's in the rejection region, and we would reject the null hypothesis. What if this were a right-tailed test? Well, if this were a right-tailed test, by symmetry, it'd be the exact same scenario. It would just be at positive 1.64. That would be the probability corresponding to 5%. So ZC would be positive 1.64 for a 5% confidence level. What if we got a two-tailed test? So let's say we want to find the critical value and rejection region for a two-tailed test if our confidence level is set to be 5%. Well, if it's 5% and it's a two-tailed test, these areas are split evenly, so it's 2.5% on each one. So I'm just going to find one of them, and I know by symmetry the other is just the opposite sign. So I would do inverse norm. Let's do the left tail. Area to the left would be 0.025. Because inverse norm is always area to the left. If I did it for the right one, my area to the left would be 0.975. Mean 0, standard deviation 1, and when I run that, I get negative 1.96. So I know this one's at negative 1.96, which means this one is at positive 1.96. So this means that any z-score that is below negative 1.96 or above positive 1.96 will be in the rejection region. It would have a probability corresponding to an overall one once you double it of less than 5%, and we would reject the null hypothesis. I'm going to give you a chance to try one. I want you to find the critical values and the rejection region bounds for a two-tailed test if our confidence level, significance level is set to be 10%. So you give it a go, come back after you've had a chance to try, see how you did. Technically, we've already done this one, because if this is 10%, that means this is 5% on each one, and that was the very first one that we did. That was the z-score corresponding to negative 1.64 from the first one, I believe is what we did. Yep, I think I rounded it. It's technically 1.645, but that's what it is. So these are, once you've done one of them, you don't need to ever find it again. The most common ones are shown here. So I supplied some of them in your note packet. We've already found the middle ones. So if you have a left tail test with confidence level set to be 10%, the rejection region starts at 1.28. And we can use these then to run hypothesis tests without having to find p-values, because we've kind of already done that work ahead of time by finding these rejection regions. The decision rule based on the rejection region is pretty straightforward. If your test statistic falls in the rejection region, you're in the rejection region because you're going to reject the null then. You have a corresponding probability that is less than the confidence level that was set ahead of time. If you are not in the rejection region, then you are not going to reject the null, and you would say there's not enough evidence against the null. So for a left tail test, if you're to the left of that critical z-score, then you're going to be in the rejection region. If it's a right tail test, you're to the right of that critical z-score, you're going to be in the rejection region. If it's a two-tailed test, if you're either to the left of the left critical z-score or to the right of the right critical z-score, then you'd be in the rejection region. Anything not in the rejection region, you would fail to reject the null hypothesis. Otherwise, there's no big changes. We are running the exact same procedure. If anything, this is almost just a review. The only difference is, instead of calculating p-values, we're going to simply compare our z-score to the critical z-scores that we found from the table supplied. We found a variety of them. The rest of them were supplied to you. All of these are just found by looking up in tables or by using inverse norm in the calculator. So example. Let's say employees at a construction and mining company claim that the average salary for the company's mechanical engineers is less than that of one of its competitors, which is $68,000. A random sample of 20 of the company's mechanical engineers has an average of 66,900. Assume the population standard deviation is 5,500, and the population is normally distributed. At 5% confidence level, test the employee's claim. Well, first off, verify we can use a normal. Well, it was said to be normally distributed. We didn't have a large enough sample. That's why it's important that the distribution is normally distributed. So the reason we can use a normal distribution is because it was stated the population is normally distributed. We're valid in using a z-score because we assume the population standard deviation is known. Now state the alternative and the null hypothesis. The null hypothesis is going to be greater than or equal to 68,000 because the alternative is actually the claim. The claim is that it's less than 68,000 because it didn't say less than or equal to 68,000. The claim is going to be with the alternative because the null always has to have the equality statement. So we're really going to be testing uh, the null hypothesis of it being bigger than or equal to 68,000. If we find enough evidence against this, then we can actually favor the claim, which is maybe a reason why the claim was stated the way it was. So step 3, we need to find the z-score so we can pair it to that critical z-score. So the z-score for our situation, the sample average was 66,900. The company's claim, well, I guess it is the company. The competitor was 68,000. That's the population mean, 68,000. Divided by the population standard deviation is assumed to be 5,500. Divided by the square root of our sample size of 20. If you run all that, you get a z-score of negative 0.89. Now we're going to determine if this is in the rejection region. This is the new step. In the prior section, we would find the p-value for this and see if the corresponding p-value is less than 5%. But we already know that for a 5% confidence level and a test that is left-tailed, we know the critical z-score is negative 1.645. If you go back here, you'd see it in our table. We have a left-tailed 5%. We need to have a z-score that is less than that, but our z-score is not less than that. It is negative 0.89. You'll see it right here. So you'll see we fall in the non-rejection region. So determine if we are in the rejection region. We are not. So I should say not we. This falls in the, what did they call it? The fail to reject region. In the fail to reject region, which means we can state our summary as follows. At the 5% level of significance, there is not sufficient evidence to reject the null hypothesis. We did not fall in the rejection region. So there is not sufficient evidence against the null hypothesis in support of the alternative. Therefore, there is not enough evidence to support the employee's claim, which was the alternative, that the mean salary is less than $68,000. So it appears their claim is unsubstantiated. And that is how you use rejection regions. It's a similar process for all of them. You run it, and you compare to see if you're in the rejection region or not, if you're above or below the critical z-scores. The honest truth, though, about rejection regions is rejection regions are really only used when teaching statistics to help cement the ideas that we've been talking about. In reality, we always find a p-value. We find the corresponding probability, and we're actually moving away from using confidence levels, and instead we're moving towards interpreting p-values in the following manner. And I have this in the classroom, actually right in the front of the room. So this will always be there for you, but we're going to practice interpreting p-values. So if you have a p-value bigger than 10%, we would say there's no evidence against the null. You found something that occurs 10 or more percent of the time, that's not unusual. If you find something that occurs between 5 and 10% of the time, it starts to be, we would say, weak evidence against the null. If you find something that occurs between 1 and 5% of the time, then we start to say moderate evidence against the null. If you find something that occurs between 1% and 0.1%, that starts to be rare enough where we say you have strong evidence against the null. This is when you can start to really make true claims in real life. If you find something that occurs with less than 0.1%, you have very strong evidence against the null, and that's when you can really start to say that you're going to support the alternative hypothesis. For today's homework, I would like you to use rejection regions. Tomorrow, you will type up an answer to a problem on the computer that I ask you to use these interpretations shown in this box right here, and then going forward, I would like you to use these inferences because that's really what people do in real life. To give some practice with it, we're going to do a couple examples. So let's say a nicotine patch claims that the average time it takes its customer to quit smoking is at most 3 months. The FDA does a study, finds the average is 4.5 months with a p-value of 0.025. What would the interpretation for that be? Well, 0.025, that's 2.5%. 2.5% is right in this range. You can see that's the moderate level. So this is what the statement would be. You would say there is moderate evidence against the claim that the average time it takes the company's customer to quit is at most 3 months, and in favor of it being the alternative, which is longer than 3 months. Second scenario, A tutoring center claims its students on average increase their ACT scores by more than 4.5 points. A study is done and found that these students increased their test scores on average by 5.2 points with a p-value of 0.0004. In this case, you would say that, value 0.0004, that's in the very strong. So you'd say there's very strong evidence against the claim that the average score increases at most 4.5 points and in favor of it being higher than 4.5 points in support of the actual tutoring center's original claim. So there's very strong evidence in support of their original claim because it's supporting the alternative, which was their claim. Going to give you a chance to try one of those interpretations. So let's say yours is a large computer repair company advertises that the average cost of removing a virus is at most $100. So at most would be $100 or less. A study is conducted and finds the average to be $101.50 with a p-value of 0.09. You try the interpretation. So you should have found that's 9% probability. At a 9% probability, that would be in the weak evidence. So there is weak evidence against the claim that the average cost for the virus removal is at most $100. So not great evidence. Probably the case that right now that the null hypothesis, that the claim, the original claim, which was the null, can stand. So that is it for today. Thank you very much.